Okay, so there's been quite a big gap between me making the last video and me making this video, so I'm just going to quickly summarise what we've done so far. So, alright, this isn't really in a very convenient position for me to write. That's better. Okay, so we took a rectangular contour in the complex plane, and we were trying to prove that Cauchy's theorem holds true for this contour. So we've got the complex plane here. We have defined a function on that complex plane, a complex function, which is going to map every value of this of the complex plane onto another value, onto another complex number, and we want to integrate that function along this rectangle. So what we've done already is we've said, well, we can divide this rectangle up into 4 pieces and take the contour integrals around each of these pieces. So in this case, this is the contour integral around here. The contour integral around this one would be here, this. The contour integral around this one would be this. And the contour integral around this one would be this. And clearly, the contour integral around the whole thing is equal to the sum of these, because if we say we will get each one of these pieces once if we had all those, the contour integrals of all 4 pieces together, and each of the middle bits, these bits here, they will cancel because we're going this way for this one, and for this one we're going this way, and that holds true for each of these 4 pieces, so they'll all cancel because we're going in the opposite direction when we integrate along this for this rectangle, than when we integrate along this, we're integrating this way for this rectangle. And of course, what we're doing is we're multiplying by dz, so in this case we'll be multiplying by a positive imaginary number, and in the case for this rectangle here, we'll be multiplying by the negative imaginary number, so when we add them together they will cancel. Okay. So what we then did is we selected a rectangle, one of these 4, such that R1, the contour integral around R1, the modulus of the contour integral around R1 was less than or equal to 1/4 of the modulus of the contour integral around the whole rectangle. And we went on. We said we could divide R1. So let's say we chose this one satisfied this property. We've proved that you could always find such a rectangle that satisfies that property, and then we said do the same thing there. Split that up and find another rectangle within here, such that if we call that one R2, then the contour integral around R2, which we're denoting eta R2, the modulus of that is less than or equal to 1/4 of the modulus of eta R1. So we can say that it's therefore less than or equal to 1/4 squared eta r. And if we continue this, we can get a sequence of rectangles, which we'll call Ri, where I is an element of the natural numbers now. The natural numbers, I don't think that includes 0, so we'll add in the element 0 there, and we'll call R0 the first rectangle, the original rectangle that we want, R0. We could denote this R0. Okay, so we've got this sequence here, and each one of the rectangles, so the next rectangle, Ri plus 1, is completely contained within Ri, and we also have the property that the modulus of the contour integral around Ri is going to be less than or equal to 1/4i eta R0. Okay, so that's what we've got to so far. Okay, so now what we want to do is we want to look at the we want to try and get an approximation for what the contour integral around an Ri f of z dz is. Okay, so the way we're going to do this is we're going to look at the function f of z, and we're going to look at what the derivative of the function is. So the derivative of the function will be f prime of z. We'll assume that the function is complex differentiable. And then what we want to do is we want to form an approximation of what f of z is. Now, how do you form an approximation of what f of z is? Well, Okay, so how can I do this? Oh, I've missed a bit. Back step, we'll go back. Okay, so a very, very important point is that this sequence of rectangles, Ri, is going to converge. There exists some point, and I'm not going to prove this because I don't actually know how to prove it, but it is a theorem that you could go away and look up. There exists we'll call it Z star, which is an element of the complex numbers. So let's say this was R, this was R1, let's say this is R2, so Z star will be somewhere in R2, and it's contained within all of them. So Z star will be contained, it will be an element of Ri for all I is an element of the natural numbers. So it's contained within absolutely every single one of them. And the fact that it's contained within absolutely every single one of them means that these rectangles converge to that. Now, how can we prove that? So what's the definition of convergence? Well, the definition of convergence is that, so we've got this sequence, R0, R1, R2, R3, and so on. So we can go on and on and on to the ith term. And the definition of convergence for these nested sets to converge to a point would mean that for all epsilon greater than 0, there exists let's call it big N, which is an element of the natural numbers, such that if little n is greater than or equal to big N, then how can we do this? Then Rn is contained within the ball, the open ball around Z star of modulus epsilon. So what does that mean? Right, so this is quite brilliant. I love these sort of definitions. They are really good fun, once you get used to them anyway. Hopefully you all have seen definitions like this many, many times before. Just straighten that out. Okay, oh, annoying. Stop it. Right, okay. Oh, that is, right, okay, that's fine. Okay, so, what that means is we have got this sequence of rectangles. So we've got R0 here, we've got R1 contained within that, so we'll call this one R1. We've got R2 contained within that one, and I can't draw any further, but R3 would be one of those little four there. Okay, and there's a point Z0 in the complex plane, and you can take any epsilon you like, and you can draw, so I'll draw another picture, you can take any epsilon you like, and you can draw an open ball around that. So this is the point Z0, this point at the centre, Z star rather, which is inconvenient notation because Z star usually denotes complex conjugate, or well, it can occasionally denote complex conjugate. But Z star means this point here, which all these rectangles we're going to say converge to. Z star, so there's this ball around there. You can take a ball around there of any radius you want, and this is an open ball. And there exists, so you can find a point in this sequence. So I can go along and I can start with this first rectangle, and I can say, so if this was the first rectangle, I can ask, is this completely contained within that ball? And the answer is, of course, no. So I go along to the next rectangle, which we'll say is R1 here, which is inconveniently drawn stupidly so that it's not the same R1 over here, but never mind. So this we'll say is R1, and we can ask, is R1 contained within that ball? And the answer is still no. And we can go further, and we can say R2 is going to have to be this one here. And we can ask, is R2 completely contained within that ball? And the answer is still no. And we can go further, and oh look, eventually, even on my drawing, R3 is eventually contained within that ball. So that's what it means, that there is a point in this sequence, there's a rectangle in this sequence, where that rectangle is contained entirely within that ball, and not only that, but all the rectangles after that specific point, after this R big N, all of the rectangles that are either that rectangle or are bigger than, or are further along in the sequence than that rectangle, are contained within that ball. That's what that says. There exists a point in the sequence such that that point is contained within, such that that rectangle is contained completely within this ball, and for all the other rectangles where little n is greater than or equal to this one, they're also contained within there. And now, that should be pretty obvious because, well, it's obvious that if there is such a point, if we can find, and I'm going to end the video there because it's been going on for quite a while, so we'll continue with this in the next video.